All right, here we go, solving this last set of related rates problems. Now, I'm going to go ahead and actually just delete this bottom one here. I went ahead and worked it out, and it's a little crazy. It involves law of cosines, and it's something that I would never give to you on a test. I just saw the problem when I was looking for problems, and it had to do with baseball, and it's playoff season, and, Mr. Crouch likes his baseball, so I had to throw it on there, and then only later did I realize how difficult it was going to be. So if you would like to work this one out, go ahead, and I'm more than happy to discuss with you by yourself the solution. I just didn't want to spend 20 minutes of the video going through how to do it when it's not something I would put on your test. So delete. All right, on to the first problem. Base of a triangle is changing at a rate of 4 inches per minute while the altitude is decreasing at the same rate. Or base of a triangle is increasing at the rate of 4 inches per minute, altitude is decreasing at the same rate. At what rate is the area changing when the base is 10 inches and the altitude 6 inches? So first thing to recognize, we've got a triangle here, but it doesn't have to be a right triangle. I'm actually gonna, that's even too close to a right triangle. I want to draw something a little crazy, maybe something a little obtuse, you might say, for my triangle here. So there's my triangle right there. And the base, well, when you're talking about a triangle, you can pick any side to be the base. So I'm going to pick this side to be the base. We'll call it B. And what do we know about B? We know from our given information there that the base is increasing at a rate of 4 inches per minute. So dB dt is 4. And we're also later on in the problem, it says we're trying to figure this out exactly when the base is 10. So B equals 10. All right, now the altitude is measurement from the opposite vertex of the base. So that's right there, opposite vertex of the base, all the way perpendicular to the base, or perpendicular to the side of the base. So the altitude goes right to here. So this segment here is the altitude. Even though it looks kind of silly, that's the way it is. That's a base and that's an altitude, so I'm going to call that A, lowercase a for altitude. There we go. Now, we know that the altitude is decreasing at the same rate. So that means over here, dA dt is -4. Now that's important right there. It's -4 because it's decreasing. And similarly, we were told that we want to find this rate of change when the altitude is 6 inches. So when n equals 6. Now, I'm asked to find the rate at which the area is changing, so I better throw up a nice little area formula here. Area equals, now I know you're used to 1/2 base times height, but it's the exact same thing. It's 1/2 base times altitude. The altitude is the height in any given random triangle. The altitude is the height. Okay, so I want to know how fast the area is changing, so I better start taking some derivatives here. So dA dt, and now here's the important part that people tend to mess up. It's b times a. B and a are both functions of time. They're both changing over time. So I've got to do the product rule with these two things. So I'm going to get dB dt times a plus dA dt times b. And now let's see. I'm trying to solve for dA dt right here. That's what I want to get. And I've got a dB dt, I've got an A, I've got a dA dt, I've got a B. I've got everything I need. I just have to plug on in. dA dt equals 1/2. Now dB dt is 4 times A is 6 plus dA dt is -4 times 10. All right, now all I have to do is simplify. Let's move down a little bit. All right, so dA dt is 1/2 times 4 times 6 is 24 plus -40 gives us -16. I think that's right. -16. So dA dt is -8. And its area here, let's see what sort of units we're working in. We were working in inches and minutes. So dA dt is going to be inches squared per minute. All right, I'll scroll back up if you want to see all that. So I guess you could just pause and rewind. On to the next one. Cylindrical reservoir is 10 feet high and 10 feet in diameter. Cylinder. Oh, I'm going to move it over a little bit. Wish I could draw good shapes. There we go. Yeah, that one's real good. So how do I make this look better? Like that, maybe? I don't know. Sure. Looks good to me. 10 feet high and 10 feet in diameter. So I'm going to put those measurements in. There's that. That's D. And I'm going to put diameter equals, well, I'm just going to wait here for a second. 10 feet high and 10 feet in diameter. And water flows in at a rate of 1.5 cubic feet per second. So water's coming in here at 1.5 feet cubed per second. And we want to know how fast is the water level rising. So we've got to think we've got some water in here. We've got some water in here. We want to know how fast is the water level rising? How fast is this height here changing? So we've got, let's give this a variable. Let's call this h. That's the height we care about. I don't really even care at all how big this cylinder is. I just care how fast is that water height rising. So let's call that h. Let's say h is unknown. And dh dt is unknown. But that's what we're trying to find. So I'm going to put that right there. Now, what else do we know? We know that, I'll go with red. We know this right here. This is going to be useful for us for the problem. We'll call this the radius of the water. We know that the radius of the water is, since the whole thing's a cylinder, the water's obviously going to fill up the whole shape. The radius is going to be 5 feet. And now dr dt. This is where it is important that you that's a beautiful D, isn't it? It's where it's important that you understand what drdt means. Drdt means the rate of change of the radius over time. So think, as this water fills up, this radius here, how's that changing over time? Well, it's not, because the water is still going to be in this cylindrical shape. So the rate of change of the radius is 0. Now, I think that's about all the given information I can think of. Oh yeah, we should put this blue about the water going in. We know that dv dt, that's dv dt, is, I'm going to put 3 halves, 1.5, and v, well, I don't really know. Okay, so we've got a lot of information about volume, about radius, and we want to know about height. That should lead me right away to think I want to use my volume equation for a cylinder. And the volume equation for cylinders, take the area of one of the faces, so that's pi r squared, because the faces are circles, and then multiply by the height, so just h. So now remember, this volume formula we're using right here, we're doing the volume of this water, which will be in a cylindrical shape because it will conform to the container. It will be in its own cylinder here. Okay, so let's take the derivative. dv dt equals pi, and then I'm going to have to do product rule with r and h. So I get 2r dr dt times h plus r squared dh dt. Now let's see, we're trying to solve for dh dt, so I'm going to put a nice little box around that. Let's see, what else do we have to plug in for? We have a dv dt, we've got that. We have a dr dt. We have an r. We have another r over here. And it looks like we're missing an h. Oh no, what are we going to do? How are we going to get an h? Well, we don't have a volume to plug back into the volume formula to get an h. What are we going to do about that h? Well, and hopefully you've noticed by now, maybe you've thought about what you're plugging in. This is a big red flag here. Not a red flag, but like green flag. Green flag meaning go. this dr dt being 0 might help us out, because when I plug it in here, guess what? There's going to be no more h's there. So let's just go ahead and plug right on in. So dv dt equals pi times 2. I'll go ahead and do it just for fun. Plug all this stuff in to show you. 2 times 5 times 0 times h plus r squared dh dt. Yeah, kind of running off my screen real estate here. Okay, so now we just have to simplify. This goes away. So I've got dv dt. Oh, don't I have a value for dv dt? I do. I should plug that in as well. I should plug all my stuff in. dv dt equals 3 halves. So we got 3 halves equals, oh gosh, I'm real bad at plugging things in. This was r squared, and r was, let's look back up there, 5. So 5 squared. So I got pi times 25 dh dt. So I'm going to divide both sides by 25 pi, and I get 3 over 50 pi equals dh dt. And then finally, I've got to do some units. So dh dt, that's the height. That's going to be a one-dimensional thing. We're talking about feet, and we were talking about per second. So feet per second. Feet per second. All right, fantastic. Let's go on to the next one. Plane is flying at a 1 mile altitude. Plane flying at 1 mile altitude, that's how high it is off the ground, is 2 miles distant from an observer measured along the ground. Okay, now here's you. Wow, you're looking the wrong way there. Let's see. Draw a nice little stick figure. There's you on the ground. And the plane is up here. Let's see, how do you draw a plane? I gotta do the wings here. Something like this. Oh, that's actually better than I could have ever expected it to be. So, most beautiful drawing ever. So the plane is 2 miles away from you across the ground. So this is going to be 2 miles, but it's also going to be changing. We'll give it a name. Let's call it G for the ground distance. We'll call this G, and then it is exactly 1 mile up in the air. This we'll call H for the height. And I'll put my variables on the inside, my numbers on the outside. H for the height, 1 mile. And then this here, this extra segment is going to be helpful because the question said, how fast is the angle of elevation changing? We got to know about that angle. I'm going to call that angle theta. So let's start. We've got a picture sort of filled in. Let's start filling in a chart over here about some information that we know. Let's use green. Haven't used green yet. So G equals, that's the distance we are away from it, just measured along the ground. That's 2 miles. Now dg dt, as this scenario unfolds, is that ground distance going to be changing? Well, this plane is flying directly away from us at 400 miles an hour. So yeah, it's going to be getting farther away. dg dt equals 400. That's pretty fast. Okay, now h equals 1. Now dh dt, as that plane flies directly away from us, is that height going to be changing? No. So dh dt is 0. And then finally, theta, that's the angle of elevation. We don't know that. And d theta dt, well, we don't know that either. If we look back at our question, how fast is the angle of elevation changing? They want us to find d theta dt. That's what we're trying to find. Okay, so we've got something about this angle in our triangle right here. And then we've got an opposite side and an adjacent side. And it's a nice little right triangle. It's a pretty big right triangle, actually. It's not that little. So let's go ahead and use our tangent formula. Tangent of theta equals h over g. Tangent of theta equals h over g. So this is always my first step here. Set up our formula that is going to get this thing in it. We've got to get a formula that has d theta dt in it. We want to figure out d theta dt. We better get a formula with d theta dt in it. Okay, so I've got this formula. Before I take the derivative, I don't like quotient rule, so I'm going to multiply the g over. G tangent of theta equals h. And now I'm going to take the derivative, so I've got to use product rule here. I'm going to just scroll down. So this is g times derivative of tangent of secant squared theta d theta dt. And I'm doing my favorite thing, if you remember from my other videos. Okay, plus, and then we have tangent theta times, wow, I'm going to run out of, I'm going to do it twice in the same line. Tangent theta times dg dt equals the derivative of this side is just dh dt. Okay, so here we go. Let's look at our given information up here and look at what we've got and see what we can plug in for. So d theta dt, that's what we're trying to solve for. So that one's fine. G, we have a value of g. Good to go. Theta, I don't have a theta. Another theta here. I still don't have a theta. dg dt, I've got a value for that. dh dt, I don't, or I do have a value for that. So the only thing we're missing is a value for theta. So I did this in the last video, triple underline that. I'm missing that one. I need to figure it out. So what can I do to get a value for theta? Why, I can use that tangent equation. So let's do that. Let's go down here. Let's use green. Green sounds good. So tangent of theta equals, do I want to leave more space here? No, we'll just put it in its own little green box. Tangent of theta equals, what are our values we have right here? H over g, so I'm going to plug in my h over g. That's 1 over 2. Tangent of theta equals 1 over 2. Now, hopefully you remember a little bit from pre-calc in that in order to solve this, what you need to do is to take the inverse tangent of both sides. So that's tangent inverse of tangent of theta equals tangent inverse of 1/2. Now, tangent inverse of tangent, they're inverses, so they undo each other, and we are left with theta equals, and I run and get my calculator. And I type in tangent inverse of 1/2 because I do not know my unit circle as well as I should. And I get something weird. Maybe I should convert to degrees and not radians. So if this is in radians, it's times 360 divided by pi. Oh, that didn't work. Well, let's just leave it as that value. Right now, what I'm getting is tangent inverse of 1/2 is 0.464. I'll round to 3 decimal places for right now. Am I doing something wrong there? Tangent is sine over cosine. I don't think so. I mean, I think that's right. Okay, let's go ahead and go along with it. I'll check it at the end and come back and redo this part if I need to. All right, so now we have a value for theta. So I'm going to go ahead up here and add my check marks under O, or theta and theta. And now we're going to plug everything in. So G was 2, H was 1. So plugging it all in. G was 2 times, now I've got to take this value. This is hard to do on a calculator. Secant squared of, let's put the 0.464 here, 464 times d theta dt plus tangent of the 0.464 times, what was dg dt again? dg dt was 400, dh dt was 0. All right, time to move everything over. dg dt was 400 times 400 equals 0. Okay, so let's try this on my calculator. I want to do the secant squared part. For secant of that thing, copy paste. Control C. Hope you're playing along at home right now. Control V. Secant of that quantity squared. Well, when I use the exact value in my calculator, which you should always do, I use the exact number, not the rounded decimal right here, like I used answer. I got a very nice answer. I got 2 times secant squared of this thing was 5/4, not 5/2, 5/4 times, and then d theta dt, that's what we're trying to find, d theta dt plus, now tangent of this thing, think how we got this. Tangent inverse of 1/2 gave us this, so if we did tangent of this, we'd get back to 1/2. I don't even need to type that in. Plus 1/2 times 400 equals 0. Okay, let's solve. 2 times 5/4, I get 10/4 d theta dt, which is 5/2, but I'm not going to simplify right now, plus 200 equals 0. And then I'm going to subtract my 200 over. So I got 5/2 d theta dt equals negative 200. So d theta dt equals, divide by 5/2, negative 400 over 5, which is 400 divided by 5 is negative 80. And we're talking about how the, wow, that seems insanely wrong. Did I miss something? That seems really fast to be changing. That angle is changing very quickly. I'm gonna have to go back and double check my work on this one, but the angle is decreasing at 80, and my calculator was in radians. I guess it doesn't matter. How fast is the angle changing? Negative 80 radians per, I guess we were going in per hour, right? So because we were in miles per hour, so negative 80 radians per hour. I guess per hour that might not be that crazy, because the angle is definitely going to be decreasing at some speed, and taking it over per hour, that might increase it a lot. I'll go back to that one and check it here real quick. I'm going to pause the video and do the workout again. All right, I went and checked and did a little bit of independent research, and from what I found in all other problems similar to this, people would, go about solving the problem, and then the final answer was in radians per whatever. Now, to be honest, I find this a little interesting, given that all of the values in here are completely independent of whether you use degrees or radians. So because we could have just as easily got tan or theta to be like 26 something in degrees and plug that in there and that in there. So if anybody has any idea, wants to, play Stump the Teacher and tell me what I'm missing here, that'd be great. But I'm pretty sure after my research that this answer here is correct. If you catch any errors in any of my answer keys, please do tell me so that I can make sure that I update those. All right, let's go on. One more problem. A trough 10 feet long has a cross section that is an isosceles triangle 3 feet deep and 8 feet across. So it's like a pig feeding trough here. It's 8 feet long. Let's draw one of our faces here. It's got a triangular face. Something like this. That's our trough. And it's got a triangular cross section. That means if you like chopped straight down on this anywhere, straight through the middles, think you were coming from the side of it, and you chop down, the piece you would get out would look just like an isosceles triangle. So the isosceles triangle is 3 feet deep. So it's 3 feet deep, and it's 3 feet, and it's 8 feet across, and it's 8. All right. Water flows in at the rate of 2 cubic feet per minute. Water's flowing in here at the rate of 2 feet cubed per minute. Okay. So how fast is the surface rising when the water is 2 feet deep? So we're given something else here. We're given that the water here, drawing our water in here, is 2 feet deep. And we want to know how fast the surface is rising. Let me draw out here this front face a little extended. We've got that this is the trough, and then in there is, the water right there. And if you notice, we've got 2 nested triangles here where they share that vertex. We've got 2 similar triangles. I'm going to split them right here so we can put some measurements in them. So this top here is 8. This is 3, and over here, the depth of the water is 2. Let's call the depth of the water here 8. The height of the water. Okay, let's add some variables over here. 8 equals 2 feet. dH dt equals, we don't know how fast that height of the water is rising. But that is what I want to know, so I'm going to circle that. What else do we have in the picture? We have dV dt. dV dt equals 2 cubic feet going in. Do we know how much volume is in there right now? No, we don't. Volume is questionable. We know some stuff about the trough. Oh, I forgot to add on that it's 10 feet long. We know that. We know some stuff about that, but for right now, that's not super important because our question asks us particularly about how fast the surface of the water is rising. So let's focus on that, and we'll go back and add in anything about our trough if we need to. Okay, so here's my chart. Here's my picture. Okay, so I'm going to use the volume formula, and I'm going to be using it specifically with the water because dV dt is about the water, not about how the whole trough is changing. The whole trough isn't changing at all. We just care about the water. So the volume formula here, once again, is the area of one of the faces, 1/2 base times height, and then times the length of the whole thing. So times L, very much like the cylinder formula. Actually, the exact same setup. So dV dt equals, now I'm going to let you in on a little trick here. If you have any values in your problem that are not changing, when you take the derivative, you can just plug in the constants for them beforehand. You could just plug in the constants for them beforehand. So the base, that's the B right here is the base of the water. This thing, as the water fills up, is the length of that changing? Yes, because that triangle's changing, so we can't do it with that. H is the height of the water. It's this right here. As the water fills up, is that thing changing? Yes, obviously that's changing. L, on the other hand, is the length of the trough, or the length of the water, how far this is going to go back there and fill up with water. Is that changing as the water fills up? No, it's not. So instead of going through the hassle of doing a triple product rule here, I'm going to go ahead and just be smart and plug in 5 for L. dH dt plus H dB dt times 5. And that 5 still, no, it's not 5, it's 10, sorry. Plugging 10 for that. And then 10 still goes along for the ride. It's still a constant multiple. Okay, so now let's see what we have. We do have dV dt, the rate at which the water is changing. We want dH dt, so that's okay to not have yet. We have H, we have the height of the water. dB dt, do we have that? No. Do we have B? No. So we're missing a few things here. We're missing both the base and the rate of change of the base. Okay, two things. For getting B, hopefully you saw this setup coming a mile away and you know exactly what we're going to do because this isn't new here. We want to set up our proportion between our similar triangles. So we've got, let's see, in our big triangle, we've got 8 as our base over the base in our small triangle, which is B equals, and then 3 is our height in our big triangle, over 2, our height in our small triangle. We solve this, and we get B equals 16 equals 3B, so B equals 16 thirds. So we've got that. We've got B. Check. I'm going to put this in its own little box. Now, also, we want to get dB dt. Now, this one's going to be a little trickier. We need, we don't really have any information we haven't used. We've got dV dt for the volume equation. We can't use that again. We can't like use the volume equation to solve for this variable because it's still going to have dH dt in it. We've got to find a clever way to use what we already have. So let's use this proportion actually again. So let's go 8 over B equals 3 over, and this time let's put H in and not solve for a specific B value, but just write down this relationship between B and H, because that then gives me 8H equals 3B, which if I take the derivative of this, I get 8dH dt equals 3dB dt, which remember, I'm trying to get dB dt out of the equation. This is the other way we can do it. Other than getting an actual value for it, we're going to be able to substitute it right on out. So we divide by 3 and we get dB dt equals 8 thirds dH dt. Alrighty then, let's put this in its own little box here. Now, let's plug everything on in. We just got something to plug in there that gives us all of our variables. All of our variables we need. So dV dt was 2 and H was 2. Try to remember those. So I plug in, I get dV dt is 2 equals 1/2 times B was 16 over, wow, that's a really bad 3, isn't it? I should change that 3. Let's do that. 1/2 times B, yeah, 16 over 3 times dH dt, which is what we want in our equation, so that's okay, dH dt, and then plus, and H was 2, let's double check, just not make any errors right now. H was 2, plus 2 times, now for dB dt, I'm going to use this over here in place of dB dt, so times 8 thirds dB or dH dt, dH dt times 10. Okay, cool, cool. So I've got 2 equals, I'm going to do the 1/2 times 10, 5, and then I've got still 16 thirds dH dt, plus this one becomes 16 thirds dH dt. Let's get rid of the 5 to the other side and do some combining as well. Inside the parentheses, so 2/5 equals 16 thirds plus 16 thirds is 32 thirds dH dt, and then divide by 32 thirds, and we get 6 over 150, 160 equals dH dt, and 6 over 160 divided by 2, I get 3 over 80. And let's look back for some units here. Let's look back. And we have feet and per minute. So dH dt, the height is changing at 3 feet 3/80 feet per minute. All right, that's the end of the, excuse me, that's the end of the related rates. I hope you found this useful, and have a good rest of your day. Oh, and feel free to come and talk to me if you're interested in that baseball problem or if you found any errors whatsoever in my work.